So now we're going to take that idea of the definition of partial derivative and turn it into a computational tool for how to compute them. So the main idea that we saw in the last clip was that partial derivatives tell how the function changes as you move in a direction parallel to one of the axes. So if you're moving just parallel to one of the axes, then that variable is the only variable that's changing. All the others are held fixed. So since the other variables are held constant, treat them as constants. And when I say treat them as constants, I mean in the calculation. So let's look at the example that we had before of 4 minus x squared minus y squared, and we'll compute its partial derivative at the point 1, 1. Okay, so that's what we're going to compute. Okay, so now if I were to do it from the definition, the way we looked at it before, then the partial of f at 1, 1, or more simply written as f sub x 1, 1. Okay, so what did we do? Well, we would need to substitute hold fixed y equals 1 in the function, and then take the derivative. So we would be looking at the regular derivative, straight d dx, of the function f x comma y fixed equal to 1. And then once we take that derivative, we would evaluate it at x equals 1. Okay, so in other words, we're looking at the derivative of, and now I'm going to substitute in y equals 1, and it becomes 3 minus x squared. And then we would have to evaluate that at x equals 1. So doing this derivative, we get minus 2x at x equals 1. And so now substituting x equals 1 in there, we get minus 2. Okay, so that's straight up from the definition according to the last clip. Now, using the idea written down just above, we have another way to do it. We can say that the partial derivative of f with respect to x is going to be d dx, and we use the curly d to indicate that it's a partial derivative. It's no big whoop. And then we have 4 minus x squared minus y squared. Now, I'm going to treat y as a constant. So I'm thinking that this one right here is some constant c. Okay, so using what I knew about derivatives, they're linear, so I can break this into d dx of 4 minus d dx of x squared minus d dx of y squared. And then I can compute the derivative separately and then put it back together in the end. So let's see. So when I do this, I know that the derivative of a constant is 0. And since y is a constant, y squared is a constant, so the derivative here is also equal to 0. And the only thing that survives is the derivative of x squared, and with the minus sign, it's minus 2x. Now, we have not evaluated yet at the point that we're interested in, but that's totally fine. Right now, we have a formula for what df dx is as a function. And this one that I've chosen is relatively simple, so it doesn't show up. But in fact, df dx is still going to be a function of all its input variables. It just turns out that for this paraboloidal function that we're looking at, the x derivative is independent of y. And if you think about the way we graphed it, actually, it should make sense to you. So then we can go and we can evaluate this at 1, 1. There's no place to put the y because it doesn't show up, but otherwise we put the x in for 1 and we get minus 2, and of course it matches what we had before. Okay, so that's the way that we'll do this from now on. So for instance, I could ask you something like, can compute the x derivative of y squared sine y minus y to the 1 over y. All right, go ahead. I'll give you 1 second to compute that derivative. All right, and there's the answer. And you knew that was going to be the case because I told you to think of y as a constant. So with that idea, this whole thing here you're treating as a constant. Now, does it make sense? Why, conceptually, you're treating that as a constant? Well, let me show you a picture of this function. Okay, so here's what this function looks like. And the thing that you should immediately jump out at you is you notice that this is, in fact, a cylinder. All of these lines parallel to the x-axis, they might appear at different heights, but the function does not change as you move back and forth, moving only parallel to the axis because it's a cylinder, right? It's independent of x. Independent of x in the picture looks like all these horizontal, all these parallel blue lines. Independent of x in the formula looks like the fact that there is no x present in the formula.